Welcome to our first science seminar of the spring semester. Yay! So this is our keynote address here. So only the best make the keynote address. And we have the best for you today. We got Dr. Olafsen from Baylor. Okay? And Dr. Olafsen has a physics degree. From, physics, there you go. Physics degree from Princeton University. She has a master's in physics from Duke University. And she has a PhD in, what do you think?
Physics.
Physics from Duke University. But she's teaching as an electrical engineer at Baylor. So go figure that one out. Maybe she can tell you more about that. So Dr. Olafsen has been here before, about 12 years ago. Yeah. And she's come back because Baylor loves Laterno students. And they want to have you guys join them over at Baylor in their graduate program. Okay? So good for you guys, right? So think about that. Dr. Olafsen has lots of publications, and she also has several patents pending on this area of infrared lasers using solid-state type of diodes. So I also want to remind you that after the seminar, we'll be taking Dr. Olafsen for lunch at the Corner Cafe. So if you'd like to join us for a lunch discussion in the Joyce Room, please do. If you don't have a meal plan, just come talk to me, and I can cover your lunch today if you want to join us for that lunchtime. All right, let's give Dr. Olafsen a big round of applause.
Thank you all so much for coming today. I drove up from Baylor this morning. I'm going to talk to you about a bunch of things, actually. My interest area, and this is part of why I'm in an electrical engineering department, even though I have a physics background, but I'm going to talk about the periodic table at some point with chemistry, and you got to do some math to do it. So there's a whole lot that goes into to my work that's very interdisciplinary. And for the biologists and interest in the room and medical interest, we are interested in a lot of biomedical applications. So I'm going to try to hit a lot of highlights and touch on a lot of those things. Part of what I'm here today, as Dr. DeBoer said, is we want to recruit students. Also, we just want to meet you and have good relationships here. The students who have come from Laterno, I enjoy. Even if they're not working in my group, they're in my class, they do well. And I've just enjoyed having a lot of students from here. And so I think there's great opportunities for y'all. Christian university to another Christian university, still in Texas, things like that. So there's lots of things that I hope we can talk to you about and just pique your interest a little bit here at Baylor. I am working on a couple of grants right now, particularly one supported by National Science Foundation and another with the U.S. Army. It's called ERDIC, Engineer Research and Development Center, and I'll talk about that a little bit at the end, just as another opportunity for research there. This is a broad overview of the different things that I work on. A lot of semiconductor stuff. In particular, I like understanding the fundamentals of things and the physics and how it works, but I also like being able to tell my mom why she cares. And so the applications matter to me, which is part of the engineering bent of a lot of this. And so I'm going to talk a bit about applications in terms of things, but making semiconductors that emit in the infrared for different sensing and things. Another thing that we've been working on is integrating graphene. If you have heard of that, it's basically two-dimensional layers of carbon, and being able to integrate that as a transparent contact on our materials. Again, we're also trying to apply things to say, can we put our sensors and use in the body? And so we have relationships with cardiothoracic surgeons and neurosurgeons at Baylor Scott and White down in Temple, who say, we would love to be able to sense and tell what's going on with a clot or an aneurysm, or with the heart say, can we do some sensing to say, all right, there's a leaky valve there. Can we use your infrared emitters and things like that and integrate them to do some endovascular navigation. Could we put them at the tip of a wire that we can go through veins and do that? And so that's part of what we're interested in. So trying to do that in vivo sensing. And then we're also looking at infrared and ultrasonic sensing in soil. That's what the Army folks are interested with us now. So just kind of an overview of a lot of the projects. I'm going to talk to you more technically about what we're working on now, and then a little bit at the end. But yeah, I'll talk to you about what we're trying to do, in particular the mid-infrared and why we care about mid-infrared relative to visible or things like that. And then a little bit about crystalline semiconductor structures and how that helps us build up into making lasers. And I'll show you some experimental results and then how those feed into sensing, future work, and then hopefully just get you to consider Baylor a little bit and give you the opportunity to ask questions and look at that. So what are we trying to do directly? We're, from a science point of view, we're trying to figure out how electrons move in materials and how to do that efficiently so that we can generate light, in particular infrared light. So what do engineers want to do? They want to make things really efficient. You go, all right, I want to get the most power out, the most light out, the most whatever out for whatever energy, whatever input that I have. And so we want to do that, be able to understand that kind of fundamentally. And so we're trying to get the wavelengths that we're trying to generate are in the 3 to 5 micrometer, but I'll call it micron region. So if you think about visible light, God made our eyes to be able to see and absorb right in that 400 to 700 nanometer region. It's awesome. Now, it's also awesome that we can't see certain things so that we don't absorb and don't hurt ourselves. So being able to work out in the infrared, particularly in the mid-infrared, those are wavelengths where you guys, even sitting here, if we turned off all the lights and put on infrared goggles and things like that, you'd have a heat signature, right? And so the heat signature, the hotter it is, the hotter it is, the more it goes toward visible and things like that. But we can see infrared signatures from engines or from different things and be able to use that and take advantage of that. Now, a lot of lasers don't necessarily work at room temperature. We're trying to get them where they operate up near room temperature or close enough that we can use a simple cooler for that. And so we're working in the mid-infrared, but we're also working in the near-infrared for some of these sensing and biomedical applications because, frankly, the sensors are smaller and easier to use and insert in the body, for instance, for some of that. And then we're trying to develop our technology so we can scale it down smaller and smaller and smaller in order to do some of this mid-infrared sensing in a great range. Now, why 3 to 5 microns? Part of it, again, eye safe. And so our eyes aren't absorbing in that range. Also, that transmits well through the atmosphere. If you say, I get lots of transmission in this particular range, but if I go just a little bit shorter wavelengths or longer wavelengths, water is going to absorb or carbon dioxide is going to absorb. And so we had some experiments. We actually had some lasers a number of years ago when I was at the University of Kansas, and my students came in and go, Dr. Olafsen, the signal looks awful. We don't know what's going on. And they were emitting around 4.2 microns. Well, I said, are you exhaling? Yeah. And so the carbon dioxide in the air was absorbing the light before it got to the detectors. And so we couldn't get a good signal without kind of making a little purge tent and saying, all right, we're going to purge out that carbon dioxide so we can actually see what's coming out of our lasers. So just a rudimentary way to go, these can work as sensors. And that's really useful when you tune them to the right wavelength. So that's the region of interest, primary interest for us. Again, I just mentioned chemical sensing, so we could talk about things in the atmosphere, industrial processes. It could be detecting weapons facilities, things like that. For biomedical standpoint, I've been involved in some projects with glucose monitoring. So, all right, can we do that and help folks with diabetes and things like that and be able to have that background? So, and I've already mentioned the cardiothoracic and neurosurgeons wanting to be able to do some oxygen sensing and things like that for biomedical devices. Because things radiate, countermeasures is really useful for going, all right, I can see the infrared signature. I don't want my plane to get shot out of the air. I don't want my boat to get blown out of the water. So if I have a way to divert that signal so we don't have heat-seeking missiles or things like that, getting them and say, I'm going to paint something else. I'm going to be able to divert that. Those are useful things. So just some ideas of the different possibilities for this. Now, why chemical sensing? Part of why we would want it, because you go, we have carbon monoxide sensors in our house. Why do I need a mid-infrared carbon monoxide sensor. You may not. For other things that are farther off, though, where you needed to detect carbon monoxide, that is useful. Why? Because you can detect trace amounts. You can basically detect smaller quantities. So a factor of 100, sometimes it's a factor of 10,000 better in the mid-infrared. So if you need a more sensitive sensor, when you need it to get through the atmosphere or things like that, this is a good range in which to work. Now, what are these made of? Materials that, if I talk about this carpet or something, you go, okay, it's just kind of amorphous. There's just, a lot of molecules, things like that. There's regular crystalline structure in our semiconductor materials, and we get to take advantage of that. What happens in physics? In physics, you start off assuming everything's a point or a sphere or things like that. You assume a lot of symmetry. So it's easier to do a lot of calculations when things are symmetric. So with solids, we often assume that we have a bunch of spheres, and that those spheres are, we can pretend they're connected by rods or springs or things like that in order to connect them. But we can think about them as a bunch of points, but they're regularly spaced, and they're spaced throughout. So we can do calculations, figure out what kind of energies we get, what kind of spacings we get, things like that. Now, a lot of the materials we're interested in fall in what are called group 3-5. So if we go over here to the periodic table, okay, I gotta come around the corner just a little bit, and see group 3, what's that? That boron column, boron, aluminum. I'm really interested in aluminum, gallium, indium here. A lot of, you go traditional semiconductors, you think about silicon and things like that. They're in that group 4 column. 3-5s, you go, all right, I got something on the left and on the right of those. And so we can do combinations of the gallium and arsenide, or indium phosphide, aluminum and timonide. Those sorts of combinations are very stable. If I had a longer class and could teach you stuff, I'd have real fun on that. But those sorts of things basically form stable compounds. In fact, a silicon would form what we call a diamond structure, but if we have the elements are alternating, like group 3 on the corner here and then group 5 as its nearest neighbor, those form what's called a zinc blend structure, because zinc selenides, zinc sulfide, things like that also form in this sort of arrangement. And so a lot of the solids, not all solids have beautiful crystalline structure. The semiconductors we work with do. And so we take advantage of that. So you had a periodic table on the table, or on the wall, so I could skip that. Now, we don't just do elements, or we don't just do elemental semiconductors. We actually layer them. And being able to put semiconductors in junctions or in layers is particularly useful. So if you put, in fact, just go back a little bit. You can put impurities. You can deliberately, we talk about doping in the Olympics, right? What's doping? You're deliberately inserting impurities to gain an advantage. All right, it's illegal in the Olympics. It's not illegal here. It's useful. It's good. Okay, so but you're putting impurities in to increase the conduction in your materials, and so you can put materials in that will give you extra electrons. That gives you an N-type, or actually that take electrons away to make vacancies, make holes, make positive vacancies. That's P-type material. And so you can form p-n junctions by putting different semiconductor materials and layers together, and you can generate light diodes with these sorts of junctions. You can also create quantum wells. Now, I know a lot of you, particularly if you're in intro classes, might not have had quantum mechanics or things like that. That's okay. Let's just think for a moment about atoms. And if you've taken some chemistry, this is good, and you have energy levels, right, for your different electrons and such. I can layer materials and basically make artificial atoms, artificial materials where we can get energy levels and energy structures by saying, I've got something that has, a larger gap of material. Basically, we have valence bands, and then you go, I can excite them to higher levels. I can have something with higher energy levels sandwiching something with lower energy levels. We can solve something called the Schrodinger equation. The Schrodinger equation is one of the quintessential equations from quantum mechanics. But if you're afraid of differential equations, it's energy conservation. There's a kinetic energy term. There's a potential energy term. Those add up to the total energy. You solve that differential equation, you get the energy levels out. And so we can do that in something like this. And depending upon the profile that we have, we can get different energy levels. Now this just looks like an artificial atom, really. And so that's part of what I'm interested in, and saying, I want to create something where my electron, and this also is energy conservation, I want to generate light. Okay, God generates light. But by God's hands, I want to artificially generate light. How do I do that? I want electrons to make energy transitions and give me photons out. Basically, those are chunks, they're units of light. And so how does energy get conserved? That an electron makes a transition from this excited level to this lower level, and I want that energy, where does that energy go? Light. That's what we're trying to do. And so we're trying to generate infrared light. Now, if you remember on my earlier slide, what did we have? We had something where I had this visible region here, and then I had the infrared out here. Those are longer wavelengths of light. So I want long wavelengths of light. However, energy is inversely proportional to wavelength, this energy difference. So the bigger the energy difference is, the shorter the wavelength is. I told you I want long wavelengths of light. So I need to find ways to reduce this gap. And if there's this inherent gap, it turns out I can't have energy levels inside the gap. They have to be at or above the gap here. So we can do different profiles where we go, great, I can have electrons here, and the holes, the vacancies that they fill so that I can conserve energy are in a different layer. However, if you think about stuff, if I separate them, it's less likely that that's going to happen, that I'm going to get that transition. So another trick we can play is actually to make a W structure. Now, for those of you who are chemists and go, W, tungsten. No tungsten. This is not tungsten. This W is just the shape of the well. I basically have a double well, and that allows me to have my electrons that could be here or they could be here, and they can recombine. They can move down to fill up this vacancy, this hole, and give me light out. And so that light, that's what I want. I want that to generate, be infrared, and all those good things. So I've got my W's. I know my diagrams are getting more complicated. What are we showing here? Basically, the different materials. What did I mention before? 3,5 materials. So aluminum antimonide, gallium indium antimonide, indium arsenide. Layering these different 3,5 materials allows me to get these different profiles and get the light out. And the W, again, is just the shape of the well. And so we call this actually being able to say, I can tune these energy levels that I get by tuning the composition of the material, how much gallium, how much indium, and how thick the layers are. That goes into solving the equations, figuring out what these different energy levels are. And so we can tune that and get that. These profiles up here are called wave functions. Basically, a simple way to think about it is the probability of finding. So the blue here, that's where the electrons are. The reddish part is where the holes are, where the vacancies are. The more area under this curve, the more overlap between them, the higher the probability that I'm going to get my photons out, that I'm going to be able to make that energy transition between the electrons and holes. You can imagine if I only had this single interface where you go, I'm going to have a peak of the psi n and a peak of the psi p. I'm just going to have a little bit of overlap here between them. That's not very probable transition. But by making this W, I get a lot more area under that curve, and I have a much higher probability that I'm going to be able to make that transition and make that work. And so this idea of this type 2 and this double well, this W shape, type 2 just says the electrons are in one layer, the holes are in the other layer. The W says I have a double well. And so doing that is kind of the backbone or the central part of the types of lasers that we're studying and working on and trying to improve to generate infrared light at room temperature, high powers, and all that to make good sensors. All right, so what are we going to do? Now, I told you I want light. I got an electron, and it's going to fill this hole, this empty state. Great. And once that happens and the light comes out, then, okay, great. That's all I got. Then where does the electron go? Where does the hole go? I can recycle the electrons. I can make them skip down a staircase. And so if I make this where I have a region where, I can get light out here, and then I step and transition to another area, and I can get light out at the next step, and I can get light out at the next step, and so on and so forth, so that they basically cascade down a set of steps. That's the concept here for how this works. And like I said, in a conventional diode, electrons come in, holes come in, I get light out, but I can only get one photon out for every electron, one chunk of light, one bit of light. Here, the electrons and holes effectively are recycled, so I can get one of those photons out at each step of the process. And so it's a way to increase the efficiency of our devices. Now, this, I won't dwell on this, but again, this is kind of a detailed what it looks like. So the different squiggles are the wave functions, kind of the probabilities that I'm going to find electrons or holes in the different spots. And then you can just kind of see some of the complication of the material. Here's the W part that I showed you. This part allows you to get the electrons to move in one direction and the holes to move in the other direction, tunneling. And so that's an electronic part of it where you go, I can get my electrons and my holes to move into tunnel and to meet at the next W, at the next junction, and give us more light out. And so we can solve the Schrodinger equation and different equations in order to basically get a self-consistent picture of how this is going to work, where they're going to be, how much bias potential there has to be on there, and so forth. All right, so interband cascade lasers were first proposed in 1994, which I'm guessing is before most of you were born. And so, but they were first demonstrated in 97, and then in 98, when I was actually a postdoc at Naval Research Laboratory, we worked on these and we were able to get really close to room temperature. In the last 20, 25 years, we've been able to make some advances on them in order to increase the efficiency, but they're still what's called a droop. They still don't quite work as well as they should. I'm going to show you some curves to give you an idea of that, but basically think about it this way. I put energy in, I get light out. And so I want to be able to say, I want to basically have a really sharp, high slope for that. And say, I put a little bit of energy in, I get a lot of light out. But if it droops, if that slope's not as high, I don't get as much light out as I expect. And so we're trying to help work on these materials and help solve some of the droop problem in these. And so that at room temperature and even above room temperature, we can have more efficient materials and more efficient lasers. Now, I was showing you the W's. Everybody turn their heads this way. Okay. So if you think about it in terms of the quantum wells and things like that, now I've turned everything on its side. So now those layers, that really detailed layer drawing that I've shown you, now it's stacked. And so all those quantum wells and injection regions and things like that are here in the middle. And then I'm injecting electrons through contacts, through metal contacts here. So the materials, this is not a great aspect ratio. This is usually like 0.5 millimeter thick. And then this is really, several millimeters long, typically. And so you drive current through in this direction, and you get light out on the edges. These are called edge-emitting lasers. If you've heard of VCSELs, those are vertical cavity surface-emitting lasers. You get light out the top. These are called edge emitters. We get light out the sides. And so, again, we're trying to drive these and get the light out. This requires a lot of doping to make N-type and P-type materials, and metallization to have contact layers and things like that. One of the things we work on in my lab is actually optically pumping them and saying, all right, we're going to hit these with, to get the electrons in those upper layers, to get them in the upper state so they can make the transition and give me photons out. I could do it with current, but I can also do it with light. And so we use lasers in our lab, or optical parametric oscillators, which is a nonlinear material that allows you to get some tunable light out, actually. This is, the reason we do this is one, we can tune and pump at a bunch of different wavelengths. Two, we don't have to do all the doping. And so it makes it easier to layer the different materials. So you don't have to put metal on them, you don't have to put the dopants in them, and you tend to be able to get to higher operating temperatures. Now, the problem is you go, all right, how am I going to get the electrons up there? Well, I got to put energy in, I got to put more energy in to excite them, then they'll relax and give me the light out. So there's going to be what's called a photon decrement. I'm going to lose some energy in that process. We also need to actually absorb the light in order for that to work, and so there's a couple of different disadvantages, but this is a way to study the materials and then improve the materials later. And so just a schematic of how we do our experiments. We have a neodymium-doped YAG pump laser that pumps an optical parametric oscillator. As I said, that's a nonlinear crystal, basically a box with a nonlinear crystal that you can change the angle. And you can get two different wavelengths of light out due to what's called birefringence. Refraction, when you put your straw in your water and it looks like it bends, that's refraction. Basically, these materials, have a different index of refraction depending upon what axis you're on, what direction. So you can use that to actually get a couple of different wavelengths of light out of the crystal. And so we can do that and get some infrared wavelengths out in order to pump and study our materials. There's a whole lot more optics in there than this, but we focus it down on the sample, which we cool down to liquid nitrogen temperatures on up to room temperature. Liquid nitrogen's just below 80 Kelvin. And then we collect the light and either just collect all of it or direct it into a spectrometer so that we can see that we actually got the infrared wavelengths out that we wanted to. Now, one of the standard types of curves that we look at is called a light curve. If I were using an electrical injection, it would be a light current curve. So how much power do I get out versus how hard do I pump it? Whether pumping it is putting light in this case, so that's why it's light, or pumping is light versus current if I were injecting current in order to get things out. And so this idea of light, or light current, what do you want? As I said before, I want the steepest slope. I want to put energy in and get light out. Now there's a threshold below which we don't get stimulated emission. That's what's when lasers, you get light emitting everywhere in every direction for a while, but then you get stimulated emission along the cavity and you get a lot higher intensities out. We want the steepest slopes. When things are bending over, it's less efficient. And so this lower slope, you go, all right, I put all this energy in. Here I only got this much light out, but over here I got a whole lot more light out. So I'm looking for generating the most efficient scenarios. Here we're just looking at it as a function of the pump wavelength in order to understand the materials a little bit better. Now, a couple things. Also, the other thing I want is I want the laser to turn on sooner. This is called the threshold intensity. Wherever you go from, I basically have hardly any emission to, ooh, it took off. I'm getting lots of light out now. That's the threshold. That's the threshold. Here it's the intensity. It could be the threshold current if I'm talking about light current curves. And so I want to minimize the threshold and maximize the slope. And so you can see in this particular plot that's happening at 1900 nanometers. And so at 1900 nanometers, what happens? Highest slope, lowest threshold. And so this is just a representation of that. And we can look at that for different materials or things like that. And so one of the things we're trying to do is improve that, understand that, and try to say, all right, how can we generate better lasers? How can we redesign layer thicknesses or processing or things like that in order to improve upon that? Here's a picture of the wavelengths that we get out. And so basically by tuning the temperature, you can see that as we increase the temperature, the wavelengths get longer on these. Now, this looks pretty broad. If you go, I thought these were lasers, and I thought lasers, you get a single wavelength of light out. That is the ideal, and it's and they're very narrow for some things. This is a little bit broader. Also, my scale is blown up here so that you can kind of see what the widths are. But a lot of these infrared lasers, they're longer wavelength, so their width relative to their actual wavelength still is relatively narrow. But also this means we can also have what are called multiple modes. So instead of having a single wavelength, there is still a fairly narrow range of wavelengths that you're getting out of this material. That's kind of what we're looking at here. And so this just gives a little bit of what we would call a spectral comparison between an electrically injected version of these lasers and our optically pumped version. These interband cascade lasers, actually, we optically pumped ones that were already doped, that were already processed and designed for electrical stimulation or electrical emission. So it's kind of fun to see, all right, they actually do still laze, but they're not biased appropriately, and so they don't get quite up to as high a temperature as the electrically injected ones in this particular case. But it allows us to see, we can actually see that and look at the different processes and how the energy levels fill and things like that. Now, part of what we're doing to try to understand these materials, as I mentioned on one of the early slides, is to integrate graphene. And so the reason we're interested in graphene is a two-dimensional material. And basically it's transparent as a contact. So it's got high electrical conductivity. It's actually also got high thermal conductivity, and transparent means it has high optical conductivity too. But now, some people will say graphene is actually not very transparent, but if I look at a single monolayer of graphene, so I'm talking about a layer of carbon atoms, so kind of a representation up here like that of, I've got a layer, like basically rings of carbon atoms. only 2.3% of the light gets absorbed that's passing through that, which means 97, 98% of that light's getting through. So we can get a lot of light through that material, but still have a contact that we can use to bias the structure. Why would we want to do that? Part of understanding this idea of droop that I mentioned, say, I want, basically, when we first learn about diodes in physics or circuits or whatever, what do we think about? Basically, current flows in one direction, but not in the other direction. Same idea here. We go, okay, the current flows, I get light out, but I don't get an infinite slope. I wish I got an infinite slope. I don't get an infinite slope, but I want the highest slope that I can possibly get. Now, that, as I said, only works it's very directional. And so, but there is radiation, actually, of photons in all directions. The ratio of the directional stuff to what goes on in the other directions actually tells us something about how well the semiconductors are behaving, performing, how efficient our light processes are. Basically, once the stimulated emission starts, once that lasing action starts, I shouldn't be getting all the radiation in other directions. That should be what's called pinned. Basically, you go, I've saturated this is good. Now, I want all of my stimulated emission. I want all of my laser emission out. And theoretically, that's what happens. In reality, I still get a lot of this emission in all the different directions. But it's hard. Imagine I shine a spotlight on you, like big Klieg light or something like that, and then I come up behind and I've got a little flashlight. You're not going to be able to see the flashlight relative to the high intensity light that I'm doing there. The laser is high intensity light. We don't see the emission, the isotropic emission in all the different directions. So, because if we're looking on that same axis, but if we look in another direction, like say through the top, which is not the direction of lasing, through the surface where the laser light's coming out the edges, then we would be able to get a measure of that. So that's part of our interest in using graphene, is to be able to say, we can actually collect light out there, or we could also illuminate it through that contact. So we could pump it optically, which is kind of what I show here, through there, and stimulate the layers in addition to having a bias or driving the current through the traditional metal contacts that way. So it gives us some flexibility to do both optical and electrical measurements at the same time, which is fun. So that's something we've been working on. We have some samples that we did in collaboration with Jim Torr. Professor Torr is an eminent chemist down at Rice University, and so some of our samples we got from depositing graphene on some of our materials there, which is kind of fun. So here's some examples of, again, more light curves and getting high slopes out and doing it with and without graphene. With graphene, without graphene. And we actually saw some enhancement in the efficiency with our graphene samples relative to the samples that didn't have graphene on them. And our next step is to apply a bias there and to say, how can we tune these to get the most light out with these graphene contacts? And so that's kind of the next step in our process there. In the interest of time, I'm going to skip that one. Can talk if somebody, if it caught your eye, come ask me later. Now, I don't want to so the physicist part of me says, I want to fundamentally understand how lasers work and make them better. And that part of me is very strong. The other part of me says, I want to attach my lasers to things and help people and do good things. And so one of the things we're particularly interested in is doing infrared sensing in the body. Now some of it can be external, but some of it we're looking at attaching sensors to a wire or implanting them. So these are a couple of different projects that we've been looking at. Now, part of the interest in this is to say, all right, if we did something endovascularly, we've been looking at a material called nitinol, which, if you're familiar with that, is a shape memory alloy. And so you can heat it to a particular temperature, and it will recover a shape that you have programmed it to do. Now, there's cool, go look on YouTube. You can see cool things where you go, you have this wire, and then I heated it, and it coiled up into a spring or something like that. Here, we've trained them to bend. And so why are we doing it bending? So that we can say, I want to go through a path to vein, artery, and I'm going to get to a branch. And then I'm going to bend, and then I'm going to follow, use that to navigate. I'm going to follow along that branch, and I'm going to get to another one, bend, follow along that branch, and so forth. So we've been able to to program these different wires. And then the idea is to attach infrared sensors so that we can say, what if we got to a blockage? Could we tell from the sensing, basically doing differential measurements like pulse ox or things like that, the way you'd measure oxy and deoxyhemoglobin, in order to tell, I know that this is an oxygenated region, or it's not. And so we can look at those and do some distinguishing markers to say, do we have a clot? Do we have pooled blood? What do we have? And so we can move along and do some diagnosis. Or with implantable sensors, we're interested in this for detecting regrowth of glioblastoma and things like that. So we're working on some projects that are related to that. But we're working on basically just endovascular navigation, attaching sensors, and then looking at how we can accomplish some of that infrared sensing in the body in order to do things like distinguishing pooled blood, oxygenated, deoxygenated blood, live tissue, necrotic tissue, things like that, in order to advance things. So we have some fun projects going with these sorts of biomedical applications there. The principle here is you go, all right, well, how are you going to heat something if it's already in the body? It's already, you go, okay, well, one, we need to make sure that threshold temperature is below the temperature in your veins, right? So otherwise you go, all right, it bends immediately when we put it in your body. So the activation temperature needs to be higher than that. But I'm not going to put a blowtorch outside your body in order to heat it or something like that. So electrical engineers, we like current. And so we're going to put the current through there and use resistive heating, I squared R. And so, or V times I, however you want to think about it that. But that resistive heating, that Joule heating, is how we can heat it up. We pass that current through, it heats, and then when we want it to, and then once you turn off the current, it can relax again and retain its shape and basically just follow along the vein there. So that's the plan. We've also looked at doing ultrasound to detect the wires. Surgeons right now use x-rays to tell stuff, but if we said, all right, we want to be able to do this for combat soldiers or things like that, out in triage fields on the battlefield, things like that. And could we do this in a way that would say, all right, we can locate this and track where the wire is going through the body in order to help a soldier, things like that, in the field. And also, it's just less ionizing radiation. Even if it's not in the field, even if it was in a surgical bay at a hospital, doctors are doing a lot of x-rays, neurosurgeons, to do these types of procedures. If you could come up with a way to use ultrasound, non-ionizing radiation, instead of the ionizing radiation, it would be a nice feature and touch. Now, to do this, they don't let us stick these wires in people's bodies. Don't worry, you don't have to come to Baylor to be a test subject. We use gelatin or things like that as what we call a phantom. And so eventually we will put them in bodies in rats and then later in humans. But right now we test it in gelatin molds with tubes that are put through and things like that in order to do the proofs of concept for this. And so this just gives you an idea of our initial setup. And so I'm running out of time. But again, another project, just give you a splash of different things to come talk to me about. And so we've been able to detect wires at different points. So basically, if you label kind of all along that tube that I was showing you in the gelatin, and say, here's where our ultrasound wand is. Can we pick up the wire? Can we see the wire? Well, over here, if I'm measuring here, I don't see the wire. And you go, I see two bright dots. Those are artifacts from the top and the bottom of the tube. They're just reflections there. But as we get over here, maybe there's something. But here we can definitely see, there's the wire as it moves in the tube, as it's underneath this different slot. And so if you do differential measurements, you can actually pick it up a lot sooner. Our eyes can't always pick it up, but with the computer, we can take differential measurements between the images and pick it up. And another student worked on a convolutional neural network in order to say, can we train these and pick up the wires in there, and could do so with some nice confidence there, which was great. Now, to summarize this part of the work, which is the main stuff, I've introduced you to optically pumped lasers, and particularly these interband cascade lasers, where I get to get multiple photons down a step. And even without biasing, we've been able to get laser emission, which is kind of exciting. We've been integrating graphene on these, which also yield emission under optical pumping. We've been able to ultrasonically localize wavelengths. And the interesting thing is, if you go, what's that sub-wavelength dimension thing? Well, the ultrasound frequency is such that you should only be able to resolve, depending upon what frequency we're at, wire that maybe is 300 micrometers in diameter, 150 microns in diameter. We're able to actually resolve with these difference imaging techniques down to 100, even 50 micron wires in there, 50 and 75 micron wires. There's good, strong signal from the wire that enables us to do that, and also some additional vibration. So, all this said, this is some of the fun stuff going on. We haven't solved all these problems. There's lots of work to do. NSF and Army and things like that want us to go further with these things. And so we want to further investigate the graphene on semiconductors and these transparent contacts. We're working on spectral measurements as a functions of temperature and pump wavelength and intensity. There's lots of different variables we can tweak in order to understand this droop problem better. And then we're also headed down the directions for the endovascular navigation, biomedical device development, and things like that. And so we're working on that. I'm going to show you a slide in a moment about some of the Army stuff as well. I do want to acknowledge my collaborators from Naval Research Laboratory, where we got a bunch of the samples, Jim Torr's group at Rice for the graphene contacts, and then Kyler, Daniela, Nazifa, and Jeremy, who did a bunch of the measurements that are in these different slides. Now, the one last slide, again, back to recruiting you. So I'm going to try to recruit you to engineering, but you heard my background's in physics. I'm married to a physicist. So Jeffrey Olafsen's in the physics department at Baylor. He and I have this Army grant with ERDIC, where we're trying to, basically, the Army's interested in what goes on in that first meter in the soil, but it's kind of hard. Why would you care about the first meter? Well, one, for traversing with vehicles and things like that. Two, okay, nobody says landmines anymore. They said unexploded ordnance is the politically correct term for that. But you don't want to get blown up by landmines that haven't gone off. So being able to detect things, and even not landmines, even just being able to detect what's under the surface is really useful. And so we're applying different infrared and ultrasonic, and Jeff's also interested in what are called infrasonic techniques as well, due to cool, if you know what antlions are, and I can talk to you about that as well. How they work and are able to do sensing below the surface. And so we're working kind of on across different scales, microscale, mesoscale, macroscale techniques for measuring what's going on in the first meter of soil, and have some folks in Vicksburg, Mississippi really excited about what's going on. And so applying some of these techniques and measurements and beams and stuff for doing that. So there's opportunities in physics as well as in engineering that we would love to talk to you about. If you're interested in something else, I'll connect you to other colleagues, but just wanted to give you a little taste of infrared, lasers, semiconductors, and biomedical, all those good things today. Thank you for your time. Happy New Year. I hope you have a great semester.
I think we have a few minutes for some questions, and maybe the first question is, what stipends are you paying for your
Great question. Okay, so next year our stipends will go up to $28,000, and will continue to increase after that by $2K a year for at least the next 3 years. So, and there are hopes to get those higher. So 28, 30, 32 is in the projected future. So we encourage you to come consider being a PhD student, but there are some master's student opportunities available as well. And you can also get a master's on the way to getting a PhD too. So depending upon what you're doing or things like that, that's kind of the levels that we're looking at working on. And yeah, that's not as much as you might get in industry, but if you get trained, it can help you get a higher paying job later in industry or things like that. So those are good opportunities too.
Other questions from the audience? Yes.
What's your favorite part about Waco?
That's a good question. I like basketball, so I like going to games and things like that at Baylor, things like that. A lot of people like the downtown. There's Magnolia. There's Dr. Pepper. I don't like Dr. Pepper, which is anathema for somebody that lives in Waco, I suppose. But there's all sorts of good things like that are there. So, and there's nice parks, and Cameron Park's beautiful, and so good opportunities there. So, yeah.
Could you go into theories as to why graphene contact layer improved the laser's efficiency?
So the primary theory we have there is that in making a contact, and we can debate depending upon, basically you put a piece of paper on a book, is there really any contact there? So we should do some annealing or things like that, and we're looking at that. But that you basically change the potential due to making either a Schottky or ohmic sort of contact. And so that reshapes the energy levels and kind of biases them at the top and attracts some of the carriers in a way that shifts the energy levels a little bit and changes the bias there. And so that's the simpler, relatively simple version of that. And we're actually looking at that more deeply right now, and that's part of what we want to know. But yeah.
You discussed in your earlier slides of different methods that this could be applied in real life. One of them was air pollution. And current technology does not have a really good way to measure that in real life because it just disperses into the atmosphere. But you also mentioned issues with temperature. So how could you see this laser research being possibly used to more determine how factories are emitting different
So the temperature that we're worried about is going to be the actual local temperature of the semiconductor itself. So I'm not too worried about what's happening in the atmosphere. So the nice thing is you go, all right, I can't get close to this. Maybe I can get close to the factory, maybe I can't. But the fact that the atmospheric transmission window is there means I can be a distance off and I can shine light through it. A lot of that light's going to get through the atmosphere before it gets scattered, that's part of the advantage of this, is saying, all right, if I were at shorter wavelengths or at water wavelengths or things like that, that's going to get absorbed by the atmosphere. But I can pick up maybe some methane or nitrous oxide or things like that and do what we would call standoff detection. Maybe I could be many meters away or a mile away or something like that and be able to pick up that. And being at these longer wavelengths, I can pick up what are called more trace amounts. So I can make a more sensitive measurement of that at a distance. So.
You can see what's going on over there at Eastman.
Yeah, so you go, all right, I want to know what's going on across town. So.
In other words, so as a follow-up to that, it would be, in other words, you can have the semiconductor cooled in a air-conditioned room and sensing something that is outside. Is that
you could if you had, basically if you've got some nice calcium fluoride windows on your room or things like that. Or I would say maybe not in a room necessarily, but you could have a small package or something like that. You could have a container or something like that. And so thermoelectric coolers are about the size of like a 50-cent piece or something like that. So you can basically mount it on something that's fairly compact and have windows and things like that you can focus it and send it for good distance.
Okay. I had another question. You were talking about infrared radiation through veins and stuff. You said that it was some sort of, you said like sterilizing radiation. What kind of harm does the infrared radiation do to the body? Okay.
The infrared radiation, I mentioned ionizing radiation, I think is what you're thinking about. So X-rays are very short wavelength, high energy, and so they can do damage to tissue and things like that over the long haul. With the infrared, you're really not, the absorption is not high, and so and the powers are low enough that you're not worried about any of the deleterious effects there. So that's part of why, kind of like you go, okay, X-rays are out here. Then we come to and then looking at the ultrasound and the optical stuff and things like that. Those are not going to be as damaging.
So that's
why you're targeting.
Focusing on the
Yeah, I was going to say you had a question there.
Yeah. So you talked about how the material that bends when it's heated.
Oh, nitinol.
So that bends when it reaches a certain temperature. So is it sensitive enough that like if you travel from one part of the body to another part that's at a different temperature that could like bend it when you don't want?
It possibly. It depends. The material, basically, nitinol stands for nickel, titanium, and the null is Naval Ordnance Laboratory because it was invented at the Naval Ordnance Laboratory like back in the 40s or 50s or something. But the nickel titanium alloy part of it, you can tune that so you can change what the activation temperature is. So in principle, you could have something that, if let's say you were in like the normal temperature part and then there was a higher temperature or something like that, that could shift or change. Normally, we're going to try to have it above any of those temperatures. We don't want it too high because we're not in the business of boiling people's blood, so we don't want it too much higher, but a little bit higher than that to do it safely, but be able to make that distinction so that you don't have, oh, it bent and like now we're clogged or something like that. So that's part of the development there. So, I was gonna say we've had nothing on the side of the room. Sorry.
You're talking about using infrared detectors to look into the first meter of soil,
Uh-huh.
but I'm not familiar with any of the transparent.
So that's still, we're actually, part of what we're doing is looking at the behavior of some of the biotics and things like that in the soil. So transmission is an issue there. And so there's infrasound and ultrasound is going to be higher success and priority for that. But they're interested in some of the beam spreading, and they want to look at scattering of infrared as part of what they're interested in right now in the soil. So yeah, there's going to be a ton of scattering in the first meter. Yeah. So yeah, we're working on that and we're working on models for them for that.
If you've got more questions, our speaker will be here for a few minutes after the talk. And also, you can bring your questions to lunch. Again, we'll be in the choice room of the corner. Okay, let's thank our speaker one more time.
Thank you for coming.